Hello, my name is Kavi Dey. I'm a junior at Harvey Mudd College, and I'm presenting our paper Dense-Sparse Dynamic Time Warping for Customizing Piano Concerto Accompaniments. This paper is based on work conducted with TJ Tsai at Harvey Mudd College and Yeet Ozer and Meinard Mueller at International Audio Labs Erlangen. Automated accompaniments generally require a symbolic score like MIDI for alignment. However, this is not available for many forms of music, such as piano concertos, and is time-consuming to create. We propose a score-free approach to generating customized piano concerto accompaniments. Our two main contributions are a dataset and benchmark for studying concerto accompaniment generation, and a novel method for performing alignment in the presence of spectral mismatch, which we call DSTTW. We introduced the concerto accompaniment benchmark. This dataset contains three different kinds of audio recordings: piano-only recordings, orchestra-only recordings, and mixed recordings containing both the piano and orchestra parts. The piano-only recordings were collected by recruiting pianists and recording the piano parts in isolation. The orchestra-only recordings were taken from Music -1, and the mixed recordings were taken from IMSLP. Here is an example of a piano-only recording from Rachmaninoff's Piano Concerto No. 2, Movement 1. Here's an example excerpt from an orchestra-only recording from Music -1. Here's an example excerpt from a mixed recording which contains both piano and orchestra parts. Note that mixed recordings are generally very easy to find from YouTube or other sources, unlike symbolic scores, which are often unavailable. The mixed recording takes the place of a symbolic score and provides a reference by which the piano-only recordings and orchestra-only recordings can be aligned. The concerto accompaniment benchmark is comprised of scenarios, where each scenario consists of a piano-only recording, an orchestra-only recording, and a mixed recording. The goal in the concerto accompaniment benchmark is to generate an orchestra accompaniment track that is synchronized to the soloist's playing. While our benchmark framework can be used to study both online and offline versions of this task, in this work we focus on the offline-only version of this task, generating an accompaniment track. Our primary metric of performance is the alignment accuracy between the piano-only and orchestra-only recordings. In order to measure this alignment accuracy, we manually annotate the timestamps of downbeats in these recordings. This figure shows a block diagram of our score-free approach to generating customized accompaniment tracks. There are two inputs to the system which are shown on the left: P-user, which contains the piano-only recording, and O-accompaniment, which contains the orchestra-only recording. The output of the system is O-user, shown on the right, which contains the orchestra-only recording, timescale modified to be synchronous with the user's playing. Note that this does not require a symbolic score, but uses three kinds of audio recordings: P-user and O-accompaniment recordings as input, and M-ref or mixed recording, which serves as the representation of the musical score. The piano-only and orchestra-only recordings cannot be directly aligned since they contain different content, but the mixed recording contains both the piano and orchestra parts. So, we estimate the alignment between P-user and M-ref. Estimate the alignment between O-accompaniment and M-ref. And then infer the alignment between P-user and O-accompaniment based on these two estimated alignments. Finally, we can use our estimated PO alignment to then timescale modify our orchestra-only recording to match the soloist's playing. When using standard alignment techniques to estimate PM and MO alignments, we find that the MO alignments are quite poor and are the performance bottleneck of the system. The reason for this poor performance is spectral mismatch. the mixed recording contains lots of piano cues that are not in the orchestra-only recording, and the orchestra-only recording contains lots of rests or homogeneous regions where chords are held for a period of time. To improve the alignment accuracy in the presence of this spectral mismatch, we propose a novel alignment algorithm called Dense-Sparse Dynamic Time Warping, or DSDTW. DSDTW aligns a dense sequence of features against a sparse set of features. In our case, we align the mixed recording features against a subset of features from the orchestra-only recording that contain prominent timing cues. The main technical contribution in our work is the Dense-Sparse Dynamic Time Warping algorithm, or DSDTW. DSDTW is a variant of standard DTW that addresses the problem of spectral mismatch between two sequences. In our concerto accompaniment application, the spectral mismatch between the mixed recording and the orchestra-only recording comes from the piano part in the mixed recording that is not present in the orchestra-only recording. The approach that DSDTW takes is to identify a subset of the selected features in the orchestra-only recording that contain prominent timing cues. This set of selected features forms a sparse sequence. We then align this sparse sequence against the entirety of the dense sequence. By focusing only on the features that contain the most prominent timing cues, we can mitigate the effects of noisy or corrupted features in this dense sequence. DSDTW has 4 steps, which we will describe in the next few slides. The first step in DSDTW is to select a subset of features that contain prominent timing cues. The top figure in this slide shows a sequence of chroma features in a recording. To select the subset of features containing prominent timing cues, we calculate the total flux of in each audio frame, which is simply the L1 distance between 2 consecutive feature vectors. The bottom plot shows the chroma flux for an excerpt of the music. We can see that the chroma flux values change rapidly, with lots of spikes in regions where the chroma features are changing rapidly. Once we have computed the chroma flux values, we simply keep any features with flux greater than some threshold gamma, where gamma is selected to keep a fixed percentage of the features. In the figure on the bottom, the features with total flux that are above the black dotted line would be selected. At the end of this step, we have selected a subset of features that contain prominent timing cues. The second step in DSDTW is to compute a pairwise cost matrix between the selected features in one sequence and the entirety of the dense features in the other sequence. In the figure on this slide, the dense sequence, shown at the bottom, where you can see all the audio frames are represented from 1, 2, 3 up to the length of the dense sequence. In our application, these are chroma features from the mixed recording. Accordingly, we label the features M1, M2, M3, and so on. The sparse sequence is shown to the left of the matrix. You can see that the sparse sequence only contains the selected features from step 1. You can see that in this example, frame 4, frame 11, 12, and 13 are skipped. In our application, the sparse sequence comes from the orchestra-only recording, so we label these selected frames as O1, O2, O3, and so on. Intuitively, we expect the selected features to skip homogeneous regions like rests, silence, or held chorus. The pairwise cost matrix is calculated using a cosine distance, so each element indicates the dissimilarity between a feature vector in the dense sequence and a feature vector in the sparse sequence. The third step in DSDTW is to compute the cumulative cost matrix using dynamic programming. Unlike standard DTW, DSDTW has 2 different modes. One mode for handling dense regions, and one mode for handling sparse regions where the gaps are present. In the figure shown on this slide, the dense mode is shown in blue, and the sparse mode is shown in orange. To determine which mode to use for a particular position ij in the cumulative cost matrix, we look at the current and previous 2 elements in the sparse sequence. If these elements form a dense sequence, then we use the dense mode. Otherwise, if these elements contain any gaps, we use the sparse mode. For the 2 blue examples shown in the figure, notice that O3, O2, O1, and O8, O7, and O6 form a dense sequence. For this region, the dense mode would be used to calculate the entries shown in blue. The dynamic programming equation for the dense mode is shown at left, and simply uses the standard DTW equations. Notice that the dense mode allows for 3 kinds of transitions: 1-1, 1-2, and 2-1. For the orange example shown in this figure, notice that O5, O3, and O2 contain a gap, and O14, O10, and O9 contain a gap. For this region, the sparse mode would be used to calculate these entries in the cumulative cost matrix as shown in orange. The dynamic programming equation for the sparse mode is shown at the left. Here, we allow for transitions from the previous row with a maximum time warping factor of 2, which maintains consistency with the dense mode. For the top row of this example, since O14 and O10 have a gap of 4, we allow for horizontal jumps ranging from 4 divided by 2 up to 4 times 2. So we allow for horizontal jumps ranging from 2 to 8. Thus, the sparse mode still accounts for the gaps, but enforces the same time warping ratio as in the dense mode. In this manner, we calculate each element of the cumulative cost matrix using one of the two modes. As with standard DTW, we keep track of all of the back pointers in a backtrace matrix. The fourth step in DSDTW is to follow the backtrace pointers to determine the optimal path with lowest cumulative cost. Note that these back pointers may result in jumps when there are gaps in this sparse sequence. This optimal path determines the predicted alignment between the dense and sparse sequences. This table compares the alignment error rates of several different approaches. Using standard DTW alignment techniques, an iterative approach based on spectral subtraction, and an approach based on first performing source separation on the mix recording to estimate the piano and orchestra parts, and then using standard alignment techniques. We also evaluate the performance of our proposed DSDTW method. We can see that DSDTW performs better or on par with the best of other methods. One of the benefits of DSDTW over these more complicated techniques is its simplicity. It only has one hyperparameter compared to a trained neural network. Here is a demo of the aligned mix using our proposed method. We invite you to try out the model presented in this work yourself at our GitHub repository. Thank you for listening, and we hope you check out our paper for more details and get in touch with any comments or questions.